and he was like super clear, so clear, and really enjoyed to read. Okay, so we'll make a start. So thank you everyone for coming. So just a couple of plugs first. The first one is upcoming talks. So next week we have Jerome Green, who will be giving a talk on the state of sort of replication in psychiatry and genetics. And then the week after we have a more general talk on replication problems in genetics research by Robert Flowering. We are still sorting out stuff in August. We don't know whether to put stuff on or have a break. There may be a couple of lectures. There is one on the 15th coming up, and maybe one on the 1st as well, which will be on possibly GitHub or R Markdown. And then we're going to meet today and discuss what we're going to have in autumn, aren't we? So that'll be interesting. But today we're joined by Zoltan Dienes, or Dienes if you're British, who I've been very excited. So I've been giving people brain damage because I've been going on and on about you for weeks now, plugging this talk, so I'm really excited for it. So you've come all the way from Brighton, from Sussex University, and you're sort of interested in, obviously, Bayes, which is what you're going to be talking about today. But Zoltan is also interested in hypnosis and sort of generally improving statistical inferences in psychological research. So he's a really important ally in the open science movement, and he's written some very, very crystal clear prose on this in papers and also in this book, which he hasn't asked me to plug. But I'm doing it anyway, so you can still buy it. But it is a fantastic read, super clear, goes through the sort of philosophy side of psychology, and it's a really good read. So I do encourage you all to read that. And here's the tea. If you want to make a stab of tea. So yeah, so do look out for that as well. So I will just quickly set up. So that's recording. Do you want me, I'll make you a tea and you can. Oh, okay.
Well, good to see you all here in the well into the summer to think about how science can be reformed. And there's a particular problem we've had in really any science that uses inferential statistics. That is how you get evidence for the null hypothesis, how you get evidence for no effect. Because you see almost any paper you read or any talk you go to, non-significant results will be used to support the claim that there's no effect going on. Right. Now, the reason why we have that situation, I think, where non-significance is used in this way, even though you don't actually have the slightest idea just from the fact of non-significance whether you have evidence for no effect, is the tool we've been using, namely p-values, doesn't really make all the distinctions that we'd like to make. So having collected some data and divided the world up into H0, say no effect, no slope, whatever, in H1 there is some relevant effect. What we'd like to be able to say, having got the data, is that we either have evidence for an effect, evidence for no effect, or the evidence just wasn't great enough yet. We need more data. But when we use p-values, they do carry evidential information, but they only make the two-way distinction and not the three-way distinction that we would really like. So it distinguishes evidence for H1 from everything on the other side, but in no way makes a distinction between no evidence for an effect and evidence for no effect. And it in no way makes that distinction, no matter what the p-value is. So it doesn't matter that your p-value is, say, 0.8, really high. That doesn't mean you've got good grounds for saying there's no effect, even though it's clearly tempting for people to say that. And the reason why it doesn't give you grounds for saying there's no effect is all you have to do is increase the standard error, in other words the noise, and your p-value goes up. But as you increase the noise, that means you're degrading the evidence. Now, how can we rectify it? Well, part of the problem is that when you calculate p-values, you're only using a model of h0 to get that p-value. You're not using a model of, or any sense of, how big the effect is that you'd like to pick up. If all you're using is significance versus non-significance. But clearly, it's relevant to know what is the size of the thing you'd like to pick up, to know whether you have evidence for it not being there. So if I said, with the evidence provided by your own eyes, is there evidence of an animal being in this room, a non-human animal? It makes a difference whether that animal could be a rhino or an ant. Because it's a rhino, you say, I've got really good evidence there's not a rhino in this room, just for the evidence provided by my own eyes. But if I say it's an ant, you say, I've got no idea either way, the evidence isn't good enough. You know, I need to get down and observe the carpet rather closely, inch by inch, before I can tell you that. You see. So it doesn't matter if you're Bayesian or non-Bayesian, that's just a logical point. In order to get evidence for no effect, we need to know what the size of the thing is that we're trying to detect. So one thing we can do is you can try and solve that problem from within the constraints of frequentist statistics, I mean normal statistics, orthodox statistics. But there's another way, the Bayes factor, which I've just found more practical and more convenient. So that's the solution I'm now going to present to you. And what I want to do is to show to you why actually it's quite practical and convenient. One way of thinking about what the Bayes factor is to take the axioms of probability and presume they provide an ideal model of how our strength of belief in claims should change. Now, if you rearrange the axioms of probability, you get this equation pretty quickly. This is the probability of H1 divided by the probability of H0. So, assuming you're willing to interpret probabilities as strengths of beliefs, and the axioms of probability define the ways by which these strengths should be manipulated. This is your prior confidence in H1 rather than H0. If you collect some data D, this is what your relative confidence in H1 versus H0 should be in the light of the data. And it depends just on one thing, and that is how well are the data predicted by each of the models. And that's the Bayes factor. So the way I normally look at it is I tend to use, most of the time, I find it's useful just to use this bit of this setup, the Bayes factor, rather than thinking about my prior beliefs and my hypotheses, because that's typically something a bit more subjective and personal. So I do work on conscious versus unconscious processes, including, say, subliminal perception. I happen to think, appropriately defined, subliminal perception a priori is a reasonably plausible thing. But you could say that's my personal belief, and say David Shanks over at UCL thinks it's highly implausible that subliminal perception could exist. So if we had our strength of belief in subliminal perception along here, and that's, say, disbelief, David's somewhere over here, and I'm somewhere over here. But in the light of the data, what's sort of common to us is how much our belief should change, and that's the Bayes factor. So that says take one step in this direction, we both take one step in this direction. So in that sense, the Bayes factor is something that's relatively objective. It's how well the data are predicted by the theory relative to H0. It's objective to the extent we can make that prediction objective, and that's one thing I'd like to talk about. So if evidence is the amount by which you should change your belief, then the Bayes factor is, from first principles, the measure of evidence for H1 versus H0, or for H0 versus H1. So that can be our starting point, a notion of evidence and first principles, and then we can see how much evidence our data provide for there being a relevant effect, as predicted by theory, versus no effect. If the Bayes factor is about 1, that means you shouldn't change your beliefs at all. So that means you don't have any evidence. So when you get a non-significant result, that could be the situation. It could be non-significant precisely because you don't have any evidence at all. But clearly that shouldn't count against your theory, right? Your theory that made a prediction of the difference. And the way round I do it, the way round is put here, that how well the data are predicted by H1 versus H0. The bigger the base factor is above 1, then the more you should change your opinion towards H1, so the more evidence there is for H1. That goes from 1 to infinity. And then how much it's less than 1 is how much evidence you have for H0, and that goes from 1 to 0. Now, there's some argument about the extent to which we should use conventions. Most Bayesians are actually of the opinion, it seems, that we shouldn't have conventions. And all you do is you give the base factor and say that's the amount of evidence. In one sense, that's all that's really there. You have a continuous measure of evidence. But I happen to think that it's useful to have conventions, to have reasonable defaults that are equivalent to, say, 5% significance or conventions on effect sizes, something like that. So you don't cherry pick what counts as a relevant amount of evidence for your own needs. I mean, I'm a cognitive psychologist, and most of the time the theories involved are as plausible as each other, more or less, so it's useful to have a standard of evidence. Now, there is a standard of evidence we could use, which is the amount of evidence we have been using for the past 100 years. What has counted as evidence for us. Now, there's no one-to-one monotonic relationship between base factors and p-values. But there's a rough correspondence, and roughly 5% significance corresponds to a base factor of 3. So if you wanted to use the amount of evidence we have you using, you could say if my base factor is greater than 3, then there's good enough evidence that we've passed the manipulation check, or we've dealt with this confound, and we can move on and deal with something else. We can progress in our research program with good enough evidence. But what we gain now, which we didn't have with 5% significance, is by symmetry a measure of evidence for there being no effect, and that is if your base factor was less than a third. That would be the equivalent amount of evidence for there not being an effect. So now we can make a three-way distinction. So we can pick a threshold of evidence, and if it's, say, 3, if it's more than 3 of evidence for H1, if it's less than a third as evidence for H0, and if it's in between, the evidence is indecisive, or it's non-evidential, or it's insensitive, something like that. But one thing to remember, and this is why people are against conventions, the one thing you have to remember is these are just conventions, and it's not as if the base factor of 2.9 is really evidentially much different from the base factor of 3.1. So the best way, I think, to think about these conventions is much like you might think about standardized effect sizes, where you say 0.5 is medium, but probably none of you think 0.49 is not quite medium yet. You say, yeah, it's somewhere in that neighborhood. Well, that's how to think about conventions for base factors. There's no step change at any point, just giving you a rough guide to the sort of evidence that might correspond to something we think of as substantial or not. Now, whether there should be 3 which corresponds to whether it should be 5% significant is a really good question, and you might know there's been debates. For example, the paper that said for one-off sexy studies we should go to 0.005 significance. At Cortex Registered Reports, we've decided that a base factor of 3 or 5% significance is sufficiently scraping the barrel, the bottom of the barrel, that we should do better than that. But we didn't want to make it too hard, so we've gone for 2% significance and a base factor of 6 for our cut-offs, for registered reports at Cortex. So I actually feel a bit better with that level of evidence before coming to conclusions. But that's a separate question. So for now I'm going to take, in my examples, I'll take 3 as a cut-off to correspond to 5% significance, just because that's what we've been using. But I'm not saying I'm committed to that as what we should go on doing. Now I think Bayes factors is part of the solution, but only part of the solution to the problems we've been having and how we need to reform. But it does deal with some of the reasons why we've been having a crisis. I don't know if you've had Chris Chambers here yet, no, but his book is one I strongly recommend, both for being very clear in laying out the problems and the different solutions, and being quite motivational. So I think a lot of open science and reform, in my opinion, in terms of the people I meet, is they generally say, I agree with you, but doesn't mean that they're doing it. And I have every sympathy with that, because I agreed with many of the reforms before I was actually doing them. So a lot of the issue is actually just sort of hearing about it over and over and over again, until at some point you make a little change. And then you've got to hear about it over and over again. At some point you make another little change, and so on. That's just how it is. So the book is motivational in that sense, and perhaps making you make some little change somewhere along the line. Now, the reason why Bayes factors play a role is they deal with this particular issue that I'm talking about, and for me this is one of the big selling points of Bayes factors, is this asymmetry we've had between evidence for H1 versus evidence for H0, because that has led to two problems. One is the problem of a selective literature that highly selectively tends to publish significant results and value significant results above non-significant results. And now we have such a biased literature that if people p-hack, they don't have to, but they generally p-hack to get the 5% significance, everything pushes in one direction. So that means our literature is untrustworthy because of that. But if at least at the statistical level it's symmetric, the evidence for H0 is in as good a footing, statistically speaking, as for H1, that can help remedy that situation, that file draw problem that we've had. But there's also the converse problem, which I think psychologists engage in, and I'm sure not just psychologists, which is, so the file draw arises because if the key finding of your paper, so you wanted to show some therapy was more effective than placebo or some other standard, you'd want to get the 5% significance, and if you don't get that, you tend to bury the paper in file draw. But let's say the key result was significant. Now you can publish the paper. Now every single non-significant thereafter you find in the paper seems to be licensed to say there's no effect going on there. The effect didn't interact with gender, effect in the stream didn't. Okay, it doesn't matter if you're male or female is the conclusion, you see. But non-significance doesn't suddenly become evidential just because some other test in the study was significant. So the other problem is that will be solved is now we'll only claim there is evidence against H0 when we do have grounds for saying there's evidence against H0. So I think that's extremely important. So just to go back to this Bayes factor here, what we need to be able to do is to predict the data from H1 and H0. Now predicting the data from H0 is easy. That's what we've been doing, the significance tests. But how do you predict the data given your model? Given by your model, I mean your model of H1. How do you know what your theory predicts? That's sort of the sticking point for people. Now I'm just going to show you one way of representing your predictions. I just want to make clear that this is not the only way of doing it, but it is a way that I use most of the time. So I just want to go through with it, the features of it. And then this will be the sort of model I will use. It looks kind of funny, so just want you to feel a little bit of understanding of it, and then I'll go through how we would use that in practice. So what this is a model of, which you would never had to deal with unless you've been Bayesian, is how plausible or probable different possible population mean differences are. Or it could be how plausible different possible population slopes are, whatever it is you want to test. Now these are population mean differences. This isn't a distribution. This isn't the distribution of your data. It's how plausible on your theory or in the scientific context different possible population mean effects are. Now what I've done here is taken a normal distribution, then I've chopped off half of it. I've gotten rid of half. The half below zero. Why have I done? Well, I didn't have to do that, but I've done that because most of the time theories predict a direction. So what this is saying is, according to the theory, remember this is all conditional on your theory, the effect only goes one way. The people who got the therapy will be better than the people who didn't. Because that's what you're interested in. No, that's the theory. That's what the theory predicts. Now, it has this funny shape of starting really high and going down low. So the smaller the effect size, the more plausible it is. You might say, well, isn't that kind of funny? Well, it is simplistic, I agree. But one reason for sort of building in as simple a way as possible the notion that the smaller the effect size, the more plausible it is that we habitually overestimate effect sizes in the literature. So if we're going to get some feeling for how big the effect is we're going to look at from the literature, it might be nice to build into our model the fact that probably smaller effect sizes are more plausible than bigger ones, and that's just the most simple way you can do that. In fact, it turns out, and this is one reason I sort of became Bayesian, is the exact shape of that model doesn't really matter much. So let's make it simple. And let's just make it a little bit more difficult for us to get evidence, so that when we do get evidence from the model, we can trust it. By making things around H0 plausible makes it harder to distinguish H1 from H0. So we're going to have some simple representation. Why didn't we do it that way around? So that's why it looks slightly strange like that, but I hope it now makes some sense to you. Now what we're left to specify there is the standard deviation of that distribution, which scales the rate at which it drops down. In other words, it scales how big the effect is that we think we're going to pick up on. So what you set as the standard deviation there is the rough scale of the effect that you're expecting in this paradigm given your theory. But there's another way of getting at that if you didn't have an estimate, which comes in quite handy, as I'll come to. If you didn't have an estimate for roughly how big the effect is, the scale of the effect, is what's the biggest effect that's plausible. Because we can take as a simplification that as a normal comes down, by 2 standard deviations out, it's pretty close to 0. So 2 standard deviations out is a rough maximum predicted by this model. So if some idea of what the maximum is, and I'll show you why we often do, if we take the maximum over 2, that's what we can set the standard deviation to. Now that is the difficult part of Bayes. It's sort of all encapsulated in that slide. So if that seems odd to you, what we're really dealing with the rest of this talk is how to deal with this slide here. Now remember, it's a way of thinking you won't have to have done before. Maybe, if you did power analyses before, you had to come up with some effect size. But my experience is most people just pluck them out of the air. They haven't really thought about how big an effect they expect in this paradigm, given the exact scientific context. In any case, in power, what you really need to do, which is again most people don't think about, is what's the minimal interesting effect size. You have to specify something really rather difficult to specify. What we have to specify here is just what's the rough effect size we're expecting, which is considerably easier. Now I use a normal there. If you use JASP or the relatively new Bayes factor add-on to SPSS, or use Rauder's Bayes factor calculator in the net, or use Richard Moray's R-code, they all use the same underlying mathematics, all those other ways, and they assume something not a normal but a Cauchy. Cauchy distribution, this one here is a sort of a hat-shaped inverted U, much like the normal, so it's very similar in that respect. And you see it's got these really thick tails. That's the defining feature of the Cauchy rather than normal, is it has very thick tails. In fact, if you give it the same scale factor as the normal, the Bayes factors come out pretty much the same, so it really doesn't matter that much if you use a Cauchy or a normal. But there's something you could think about to make an informed choice between the two. Namely, I said with the normal, if the standard deviation is set to a certain value, the maximum is about twice that value. In that, only 5% of the area is beyond that. The Cauchy, that's, if the scale factor is R, the maximum is about 7R. So that's how it differs from the normal, and that's how you might think about the relevant difference in terms of Bayes factor. I don't want to sort of dwell on that. I mean, one of the perhaps the most useful take-home message is that in terms of setting the same scale factor, you're going to get much the same results, so it doesn't really matter too much which one you use. Though I prefer the normal, for reasons I can go into later, that hinges on that fact that I've just talked about, typically. So, summarise. To know what evidence there is for or against your theory, you need to know what it predicts. I hope that's self-evident. That is, you need to sort of know, because we don't, in psychology we don't predict a single value. We don't say it has to be this value. We're predicting a range. Right. So we need to know what range of values is consistent with the theory. And that amounts to specifying a model of which values are plausible and which ones are implausible. Now, what's something that's tempting and people often do is they say, well, I don't know what effect size I'm predicting here. But you know what, I've collected the data, and the best information I have for how big the effect is for this sort of paradigm is that's in the very data itself. So if I was looking for, you know, whether walking mindfulness meditation increases mindfulness, why don't I run the study and see on a mindfulness questionnaire how big the change in mindfulness was, and then that's the effect, my best estimate of the effect. Now this is what counts as cheating from the point of Bayes, because you're double counting. You're using, you've got this theory, you want to make a prediction of your effect size. So you get your data and you get a difference of 0.2 Likert units on FFMQs and mindfulness questionnaire. Then you're using that to inform your model of H1 in your Bayes factor, and then you're using it to test the theory. So you used it twice. You used it once to make your predictions, and then twice to test those predictions against the data. That isn't what Popper would call a severe test. Right. It's a very weak test of the theory, because you're maximising the fit between the theory and the data even before you try and test it. So it's very difficult to show that theory wrong if you're making it as close to the data as possible. So we can't do that. But this is the difficult issue. Okay, so I can't use the very mean difference I'm testing to make my prediction. But then people say, I don't know how I scale my Bayes factor. You know, what am I going to do? Well, what I want to show you and give you some heuristics is, even if there's no past research, you can get information from your design and aspects of your data that you can use to inform your predictions in ways that do not compromise severe testing. So I'll give you an example. Let's say theory A says autistics will perform worse on some tasks than controls, but this is, you just invented the task. You don't know how people perform that. And theory B says autistics and controls will perform the same. So here's the data. Let's say there's 0% is chance baseline, and it can go up to 50% score for this. So controls are at 10%. They're actually 2 standard errors above baseline, so the controls are performing significantly above baseline. But if you did a test now on the difference between autistics and controls, it's non-significant with a small standardized effect size. Now, most people stop at this point and say, well, clearly theory B is supported. It's a non-significant result. But you know, based on what I'm just saying, that you can't just jump to that conclusion, because non-significance by itself doesn't mean anything. Nothing evidential. You don't know what it means evidentially. What we need to do is model H1 in some way. So you say, well, I heard these Bayes factors are good, and there's something called a default Bayes factor. That's what JASP gives you most of the time. Or you go to, which is where I got that from, it would be the same as the JASP one, Jeff Rauder's Bayes factor psi, and it has filled in a scale factor of 0.7, which means a Cohen's D of 0.7, tests with respect to standardized effect sizes. So yeah, it's a sort of, I say 0.7, Cohen's D of 0.7, it's a sort of effect psychologists are interested in, you know, thereabouts. I don't know about, people haven't used this task before. 0.7 seems reasonable, it's the default. Let's just go with the default. And I see this a lot in papers. I mean, I'm really pleased when I pick up papers now and I see base factors in there more and more, particularly when someone wants to claim evidence for H0. People are now beginning to know you need something like a base factor to claim evidence for H0. But often it's a default base factor, like this one is. I haven't thought about the scientific context, I've just said, comes 0.7, sort of thinks psychology is interesting, go with that. So for these data, it gives you a base factor of 0.27. Now I don't know if you remember the sort of the conventions I was talking about, but less than a third was evidence for H0. So you say, yeah, this is less than a third. So it is evidence for theory B. All right, but let's now just think about the constraints that are implied by these very data themselves. The controls performed at 10%. According to theory B, according to theory A, autistics will perform worse on the task than the controls. That means, according to the theory, the autistics, if they're going to satisfy theory A, will lie somewhere between, should lie, if we're going to get evidence for there being a difference, between 0% and 10%. Right. That 10% is a constraint on how big a difference we could pick up. So let's say, as a simple assumption, 10% is the maximum difference we could get between autistics and controls. Now, I'm giving you a lot of information, so I'm not sure. Remember what I've put here. This means a half normal. One thing you should do when you use a base factor is specify the model that you used. Because remember what a base factor is doing is comparing the predictions of one model to another model. There's no such thing as just the base factor for those data. It depends on what the models are. Different models get a different base factor, obviously, because you're comparing how well one model predicts the data compared to another model. So it's got to depend on the models, and it should. So implicit in base factors, again, we can change this, but implicit, unless you specify, would be one of the models is H0 is 0 effect. Okay. So that means we need to be explicit about what the other model is there. So HN means half normal, with a mode of 0 and a standard deviation of 5. Why 5? Because what we're thinking here is 10 is a constraint on the maximum, and we can use half of the maximum as a scale factor. So I put in 5. That gives a base factor of really close to 1. That means there's basically no evidence here for or against theory A or theory B. We shouldn't, based on that base factor, we shouldn't conclude in favour of one of those theories yet. Now, what I have done here is I've used some information from the study to provide constraints in constructing a base factor. You might say, well, how does that fit in with what you said before about you can't use the very mean difference as the prediction for that mean difference in which it's tested? Well, first thing to bear in mind, it wasn't actually the mean difference that we're testing. We're testing this 2% difference here. That's what we're testing. We're not putting in 2% as our prediction, so we're using different information. And a constrained inference in a plausible way by taking the controls as the maximum difference between controls and autistics. It showed we have a floor effect because the standard error of the difference was about the same size as the maximum difference. Yeah, sorry, I should have pointed that out. What I put in here is a standard error of the difference, which is 8% for these data. So that's why this conclusion is quite plausible, its standard error of the difference is about as big as the maximum difference you could get. Clearly the data are non-evidential. You see. So what we've been able to say is there's a sort of a floor effect going on here. I've shown there's a floor effect. And that's the standard error of the difference. That's a sort of flaw on our difference. We need to be able to get differences much bigger than that. But we're constrained by this. This is our maximum difference. On the other hand, if we just collected more data and our standard error of the difference became tiny enough, which we could do just by running more data, we can now severely test the theories. You see, if the autistics had been close to controls, we could have got good evidence against the theory that predicted the difference. Conversely, if the autistics had been very low and we had a small standard error of the difference, we get really good evidence against the theory that predicted they were the same. So by using this as our maximum, we haven't compromised severe testing at all. We can get really strong evidence against either theory by using this heuristic. So using some information from your very own experiment need not compromise severe testing. Okay. So therefore it's legitimate to use that information, those constraints embodied in your own data, in order to generate your model of H1 in order to draw plausible inferences. I just want to show you something else I now do whenever I do a base factor. So, first thing, I specify what was the distribution, half normal. There was this standard deviation 5. People see that, they know what the model is. But why 5 exactly? Then there was just sort of simplifying the assumption in a way to say 10%. That 10% is just an estimate. It's not a population value. So we've just taken a simple assumption to get this 5. How sure are we our conclusions depend on that scale factor standard deviation being exactly 5? So what I do is calculate something called a robustness region. I vary this number, the standard deviation, as small as I can, as large as I can, such that I draw the same conclusion. In this case, the conclusion is insensitivity. The base factor is between 1/3 and 3. It's in that region around 1. How much can I vary the standard deviation and still say insensitivity? That's how robust my conclusion is. I mean, robustness checking is something you should do for any sort of modelling, whether it's Replication or Bayesian, but this is an easy way of doing it in the Bayesian case. This is sort of, I don't know if you know the term multiverse, this is sort of like a mini multiverse. It's performing a set of analyses to say which set of them draw the same conclusion. But it's sort of easily done. Now, a standard deviation here in the base factor, I use raw units. This 5 is in the same units as my dependent variable. That means 5%. These are standard deviations, limits that produce insensitive evidence. They're in raw units, 5%. Sorry, percentages. Percentage correct. Now this is 28%, standard deviation of 28%. I'm still getting insensitive evidence in this case. Standard deviation of 28% means a maximum of 56%. That's off the scale with this task. So I told you the maximum is 50%. So that means this is robust. My conclusion is robust. It did not depend on precisely this value. Any scientifically plausible value would lead me to the same conclusion. So therefore I say, I accept it. And that gets around one of the key criticisms of Bayes is to say, yeah, but your results depend on your prime, rather than my model of H1. Of course, your results aren't guaranteed to be robust, but if you always report a robustness region, people can see how robust your results are. So, I've one rule, by the way, I've had for some years, which is a P for every P. I'm trying to do it through effects. I do report p-values, but I also, wherever I report a p-value, I report a base factor. So now, just starting now, I'm not sure it's in the published papers yet, maybe some just out. I also give this robustness region, that way, for every data. So people can see how robust the conclusions are. So what we need for a heuristic, like the heuristic we used here, is a value that puts us in the right ballpark. So what I want to say is 5% isn't necessarily precisely the exact value that must be right, but it's in the right ballpark. What the heuristic we've done of taking half of 10% is giving us a value that's in the right ballpark. Then we use the robustness region to check how robust it is. And if that robustness region, as it is here, is the width of a ballpark, then we've said we've done our job. So I hope I've now covered the meat of what I want to say. I just want to go through details of how to generalise what I've been saying. So I hope you're keeping up. I think every point is understandable, but there's a lot of points. So,
Zoltan,
yeah.
just on your slide just before, how do you deal with compound performance, where a very slight difference between two groups adds up over time to a large difference? So, like the study of mathematically precocious youth, they've looked at the top 1% on maths when they were tested when they were 13, and then they found they outperformed the rest. And then they've drilled down into the top percent and looked at the top 0.1%.
Yeah.
So they're scoring not much higher on the maths test. And they found that they, over time, they actually have more patents, they earn more money, generally outperform them.
Yeah.
So how would that fit in with the sort of your evaluations of meaningful results?
What I'll do there is, so what you're doing is you're taking successively higher percentage values. I'd have to think about it a bit, but the thought that comes to mind is each time you're expecting smaller and smaller differences. So a previous step might define the maximum difference you could expect on the next step. And then that defines a range within which you could expect differences on the next step. And then that could be your model of H1.
Yeah, because at the moment of testing, they all do test at 13. There isn't much between them. It's a Sigma paper. But by the time you catch up with them when they're 40, they've diverged.
Right.
And so it isn't, it's just like a really interesting perspective on your work.
Yes. So maybe I would think, I'd think of some way of constraining the maximum difference that could be, which you might be able to get from the rest of the data, and then using that in a model like this. Something else I would say as well is I wouldn't necessarily always do a base factor, just like I wouldn't always do a p-value. In other words, hypothesis testing might not always be exactly what you want to do. Sometimes there's two versions of inferential statistics, or two roles they play. One is hypothesis testing, the other is estimation. Sometimes all you might want to do is estimate. You just say, here's a confidence interval or a credibility interval, and the effect size, you just leave it at that. If you do that, you would never be entitled to draw the conclusion there's no difference. Just to bear that in mind. If all you do is estimate, you can never say you have evidence or grounds for saying no difference. If you want to say there's grounds or evidence for saying no difference, you have to do hypothesis testing in some form. So then you need a model of H1 and do a base factor. So I want to generalise what I've talked about to say there's some heuristics which are useful, which you can, all of these, and there's others like this in the paper that's just about to come out, in that new APS methods journal, AMPS. They all have all these heuristics have a common feature that you can use them when you have no prior information, like in the autistic one. I've just been talking about. So first of all, I'll take the very heuristic I used in the example I just gave you, and I'll call that the room to move heuristic, because what the control group told us was how much room do we have to move in terms of the difference between the groups. So we can treat that as a general principle. So here's another example. In fact, I often use this heuristic, but just to get another example, there was an issue of some journal, I can't remember, in 2017 that was just dedicated to looking at replications of the power posing effect. And this particular paper looked at an older paper. Well, what they did was they had people were interviewed, and in the interview, raters then rated how dominant the person seemed in the interview. The manipulation was just before the interview. The subject either held an expansive pose for a minute or a contracted pose for a minute. And the question was, did that make them more, did they feel more expansive and big and so on, and become then more dominant while being interviewed? And they could estimate the difference of 0.66 units on a 1 to 5 scale. So in the replication, everything seemed exactly the same, except they used a 1 to 7 scale. Otherwise, everything is the same. This was the mean for the people who should have high dominance, the mean for those who should have low dominance. So it's very small and non-significant. Well, non-significant by itself doesn't mean anything, so we need to say, what do we predict? Now, in the case of replication, this is why I looked at a replication issue. There's sort of a straightforward thing you can do, which is you look at the past effect size. Because you can say, the theory I'm testing is, the theory given in the methods by the original paper produces the sort of effect size that they claim they got. That is the claim of the paper. That's sort of a low-level theory, if you like, that the paper in effect makes. You do these methods, you get this sort of effect size. I can show you another little trick here. So they had 0.66 units on a 1 to 5 scale. We'll just multiply that by the scale lengths. They will stretch it out, contract it, because the scales are virtually the same. They're just contracted or not. Actually, I made a mistake on this slide. 7 over 5, this is something you could easily make, because that's 7 and that's 5. But in fact, the length of that scale is 4, and the length of that scale is 6. So notice I've corrected that on the next slide, but forgot to correct it on the previous slide. Anyway, that's quite useful, because then you'll bear that in mind when you do it yourself. Okay, so now one reason I picked this is we have an estimate that would really be the best one to use. But let's say we had no prior information. Let's say there wasn't that previous study. What can we do? Well, we can use the room to move. We can say the low group scored on dominance 4 units on a 1 to 7 scale. So the room to move we've got for the high group to be better than is 3 units. So that's the room left we've got to move. So that's the maximum difference. So we use a standard deviation of half the maximum, which is 1.5. Now in this case we can compare the base factors we get. This is from using the past study, 0.27. It's actually good evidence for the null. This effect doesn't occur. And we have good evidence for the null using the room to move heuristics. So they qualitatively agree. This here is the robustness region. Reasonably robust, but if you had grounds for thinking the scale of effect be less than 0.8, you might not regard this conclusion as very robust. But you can think of, and I get this notion from Karl Popper's notion of corroboration, your claim of evidence is just a sort of a summary of the state of debate up to this point in time. In other words, there's no final claim to this is what the evidence is, full stop, in that sort of sense. If in some future people have good reasons for thinking a scale of effect should actually be less than 0.8, you would revise evidential claims, I think, and so on. Well, my main point is that the room to move heuristic can function reasonably well in cases, and we can check it, in cases where we actually have an informed estimate of the effect size we'd like to use. It's particularly useful in interactions. So one of my areas of research is hypnosis, and Amir Raz, who was in Canada at the time, came up with this suggestion that you give highly hypnotizable people, where you say, when you look on the screen, you'll see patterned in a meaningless script. Foreign script you don't understand. They'll have no meaning to you. In fact, it's words in English, and you give them a Stroop test. And his claim was, without the suggestion, let's say you get a Stroop interference effect of 50 milliseconds there. So in other words, when this is no suggestion, that's when the word is neutral, like lamp, and that's when the word is opposite to the colour, different colour to the colour the word is presented in. You're slower, that's 50 milliseconds different. You give the suggestion and you substantially reduce the Stroop effect, approximately half it. I didn't actually believe this when I heard about it, but as of about 6 years ago, I ran lots of experiments with it, and I replicate it. Not only do I replicate it, I basically replicate it every time I run the study. So I have to believe it, even though it seemed to contradict my own theory of what was happening hypnotically, so that made it interesting to me. But let's say this is the very first time we run the study. So we don't have this information that the suggestion approximately halves the Stroop interference effect. What could we do? Well, the Stroop interference with no suggestion is 50 milliseconds. By how much could we reduce Stroop interference? Well, by 50 milliseconds. That's a room we have to move, right? So there's a room to move, heuristics. So use a half normal with a standard deviation of half of that, 25 milliseconds. So you can use an interaction where you're predicting a direction like that. You can use this one simple effect as a maximum for what the interaction could be. If the other simple effect is going to vary between 0 and the first one. Now another sort of relationship researchers are interested in, not just differences but correlations or regressions. Just as I prefer raw units in doing differences, I prefer raw units, raw regression slopes in doing relationships, association. As you see, if you look at my paper is called How Do I Know What My Theory Predicts, which is on my website. I'm just going to put the final revisions, cosmetic revisions, up on it, and then it'll come out. A general theme through all my examples is I actually think it's a lot easier to know what you predict when you deal with raw units. Now the real reason researchers went to standardise units like Cohen's do was I thought it would make it easier to make predictions. I think it makes it really difficult to make predictions. I mean, what Cohen's do you expect? I mean, what correlation, 0.2, 0.3, in a particular scientific context. But when you look at the raw slopes, raw differences like we've been using, I find it a lot easier. And not only that, I feel much better staying close to raw units, because I think as scientists we should care about the units in which we measure things. And if we get rid of our units as soon as we got them and standardise everything away, and you've got no idea what the size of things actually are, then I think we've lost something. So here's a paper I found where, for various theories that they quoted, they looked at men and women, which could be high or low in marital satisfaction, and they had people rate how much they thought the partner was suffering on a given day, and how distressed they themselves felt in the marriage on that day. So we look at the relationship between how much marital distress the person is feeling and how much suffering the partner is feeling. Now the claim from various theories, which I can't quite remember how it went, was, if I put the quote here, that only for women high in marital satisfaction would you get this relationship between marital distress and partner suffering. Okay, so let's see how we can get an idea of how big an effect we predict. Well, let's say, often the way to think about this is imagine an ideal world where the only causal processes operating are those postulated by your theory. How would things look? Well, in an ideal world, if your partner suffered terribly, 10 units on this scale, and you're sensitive to them, you'll be very stressed. So that's a 4. And if your partner did not suffer at all, that's the bottom of the scale, you wouldn't be stressed. If this was the only variable that was in operation. Okay. So we'll bear in mind that it's ideal, but those seem plausible matchings of a high value and a low value given the theory. Well, then a perfect slope is that one. We just connect the points, and it's that difference divided by that difference, which gives us 0.33 distress units per suffering units. But notice that would be ideal, right? So that's a maximum slope that we could expect. So we can use maximum over 2, we use a scale factor of 0.17. Now for high satisfaction women, I had to go to the graph to get the raw slope. Even I noticed in papers where they claim slopes are particularly difficult for researchers, I think. Often I don't know if they really know what they're reporting when they give a number for a slope. Even when papers claim to report a raw slope, when I look at the graphs, I say that's not a raw slope. But I looked at the graph and I could see that I could measure the change on the graph. Fortunately, I did have a graph of exactly this. It was 0.22 distress units per suffering rating unit for the high satisfaction women. That was the actual sample raw slope. Now, for me, that struck me surprisingly high. That's pretty close to some ideal maximum. Which is kind of implying that the major causal process operating is this very one that they were talking about, is how much their partner was suffering. They were just maybe empathically relating to, and it was a big, huge determinant of their distress. So they had a t-value of 3.06, which is significant. We can do a base factor on that using this ratio of scales heuristic, I call that. Because we've divided the length of one scale by the length of the other scale. We check that that's a theoretically appropriate thing to do. And this is robust. That goes from a tiny slope to a slope that, remember, 0.33 was the maximum in an ideal world, and this goes up to a slope of 6. So this conclusion is robust. The heuristic has put us in the right ballpark, and the robustness region has shown the ballpark covers it. Okay. We only needed to be put in the ballpark because the same conclusions follow no matter where you are in that ballpark. But now we're going to do something interesting. Having shown we can get the same results with the high satisfaction women as they got, we can look at the high satisfaction, marital satisfaction males who had a non-significant slope. Apparently males' marital distress doesn't depend on, even if they're highly satisfied with their marriage, how much suffering their partner is having. Now, I wondered about this conclusion. And they claim, from this non-significant result, they drew the conclusion of a non-relationship here. But in fact, if you do the base factor, it's insensitive, it's close to 1, with a large robustness region, bearing in mind 0.33 is the maximum. So actually, it's really quite useful. We have a robust conclusion that is insensitive to the prior over a model of H1 over any reasonable value of a form of it. That says these data are insensitive. Don't be so hard on males yet. We haven't established the case that they couldn't care less about the partner's suffering. But if you look at the conclusions here, this is a t of 3. I haven't put the p-value, but it's really pretty significant. So they get a low p-value in the case they said there will be a difference. And this is pretty non-significant, if you see. That's a tiny slope. Okay. But that non-significance does not justify the claim of no effect. Okay, I've been going on for
I'm just going to
some time.
Well,
So
I can say if I have, but I don't know about you guys. So if you do, it is past the hour, so if anybody does want to slope off, you can, or how long do you reckon you are?
well, actually, I can stop it because I made my point. I just wanted to show you that.
Well, no, I don't want to stop you. Please don't. So yeah, it's just an opportunity for people to get, because I don't want people to be detained out of politeness. Okay, we'll carry on. I mean,
let me give you just one more example then of a heuristic. So here's another one. Let's say it's what I call the ratio of means heuristic. So in this case, we had a plausible maximum we could sort of theoretically determine, or high value, plausible low value we could sort of theoretically determine. It's not always like that. If you have a dependent variable like reaction time or d prime, it just goes off to infinity. So what's your plausible high value? Let's say you take a case, because implicit learning has actually been my main research area, so the notion you might acquire unconscious knowledge. So what you want to do is show people come to perform better on some task. Let's say you measure reaction time, but you want some measure of it being unconscious. So it might be some d prime or discrimination measure is your measure of consciousness. And so this is often done. What people do is they say the relationship between performance and the measure of awareness is non-significantly different from zero. So performance doesn't depend on awareness, so it was implicit. So what we want here is we need evidence for H0, and clearly a non-significant slope in itself won't do its job. We need to be able to say how big a slope could you reasonably expect. Now here I just show you a simple trick. We don't have a high value, but we have the means. So we can say, given this is the mean d prime and this is the mean reaction time, on the theory that there's only conscious knowledge going on, both this performance measure and this d prime measure reflect conscious knowledge. So they go down to zero together. So if you're a person who wants to say there's only conscious knowledge, you predict a size of slope there. Okay. It's going from mean to 0, 0. So that sort of ideal slope is that value divided by that value. You see how difficult this would be if we just said, what's Pearson's correlation coefficient we predict on the theory? 0.2, 0.4, 0.5? I don't know. You could look at the reliability of the measures, and you should do, but given the limits of the reliability, what do you expect? Let's say they're perfectly reliable. I don't know. But if you think in terms of the raw units, you can get an answer. So, actually, I'll leave it at that. Okay. I just want to show you, and if you go through my paper, you'll see other little tricks like this. That getting an idea of how big an effect you predict isn't actually so difficult. And that is the one thing I think has been holding people back from using base factors and say, what does my theory predict? I don't know. Well, you can cheat some information out of your own data, even in the absence of prior information, to constrain your predictions in useful ways that do not compromise severe testing. So that's my message. All right. Thanks very much.
Any questions for anybody? Well, I'll just on.
Thanks for a really, really interesting talk.
Cheers.
I just wondered, is there an equivalent within this framework to the multiple comparisons issue
to deal with multiple comparisons, there's actually a couple of issues, but I think the one that often comes up is, let's say you're interested in, do meditators have better attentional abilities than non-meditators? And we'll do an EEG study and compare them, and there's various EEG components that related to attention. Could be ERPs, or it could be some rhythm or other. And then multiple comparison issue comes up because people hunt through all these different ways you could get at attention, and then they say, oh, well, there's this one, and we'll report that and say, look, meditators have better attentional abilities than non-meditators because it came out on this one measure, but the other 20 measures you could and did test got non-significant results. So that's a problem, right? It's a real problem. Now, the way I deal with that is to think about what are all the different ways, what are all the different tests and comparisons which are relevant to your theory. And just because some rhythm seemed relevant to your theory and that came out significant. What about this other measure? What about this other measure? What about this other measure? This is where pre-registration comes in handy, because you can think about, without being led by the results in terms of what you want to believe, think about all the different measures that would be relevant. Then what I'll do is I'll get a Bayes factor for all of them, and then a summary Bayes factor that combine those all together. That way, if you have one measure that comes out in favour of meditators having better attention ability than non-meditators, but all the others were non-significant, when you get your overall Bayes factor, that could well come out saying, no, there's no difference between them. So the point is to take into account, and this is sort of true on any sort of philosophy of statistics. You need to take into account all the evidence that's relevant to your theory, and I think that's a key situation where the problem of multiple comparisons comes out. That people cherry pick the one way of thinking about the evidence that they think supports the theory. So Gelman, I don't know if you know the Garden of Forking Paths paper that Gelman and someone else has. What he did was, which I thought was neat, he looked at some papers where he looked at the predictions of the papers, given the theory. And he said, well, these predictions seem rather complicated. If you thought about the theory from first principles and derived your prediction, you come up with a simpler prediction. But the simpler prediction in all cases had not come out, and the more complicated one had. And what's interesting about that is Gelman could see in retrospect that that was true. So people had cherry-picked the comparison, and it's kind of obvious even in retrospect that they cherry-picked the comparison. So there's a multiple comparisons problem. You should have thought about all the ways, all aspects of the data that are relevant to testing your theory, and taking them all into account in the overall evaluation of your theory.
Just piggybacking on that, imagine you've got a PI who wants to peek at their data on an optional topic and all that. Does Bayes deal with that?
Yeah, so two things. Optional stopping isn't actually a problem for Bayes. So you can run until you get a Bayes factor greater than 6 or less than 6, for example. So you can peek at the data. And that aspect. So what's a questionable research practice for frequentist statistics? That precise one is not questionable for Bayes factors.
Do you have to update the prior as you go along?
No, you just keep your same model, and then you just use that.
You test it on X number of subjects.
Then you run 10 more and you test on that.
And that doesn't.
And that's fine. Yeah, but there still is an analytic flexibility problem, which you can get if you peek at your data, and that is the one of, well, all the analytic flexibility that applies other than optional stopping, but the other things like how do I get rid of outliers? Do I put in gender as a factor or covariate or something? All of these will push your Bayes factor around as well in exactly the same way. Exactly which contrast am I going to take is crucial for my theory, or which dependent variable is going to be the do I believe about this condition? All of those things, they apply to Bayes factors as well. So Bayes factors don't preclude the advantages of registered reports and pre-registration. So they're only sort of part of the story. So one would still need to, one should pre-register the test or contrast you're going to use to test your theory, and think about that. But the one advantage is you can say I'll run until my Bayes factors more than 6 or less than 6. You don't have to specify there'll be 50 subjects and then I stop. Bear in mind, and this is something E.J. Wagemakers has said, the only people who treat evidence as fixed for all time once you've collected the pre-specified number of subjects is frequentist statisticians. What about children learning a language? They keep updating the evidence as they hear it. Animals learning anything, us learning anything, riding a bike or whatever. Evidence is something you can continually update and learn, and it has to be that way ultimately. And that is the nature of evidence. And if you have a proper measure of evidence, it does behave that way. And because Bayes' factor gives you a proper measure of evidence, it's something you can always look at any point in time. Because the p-value wasn't actually quite a proper measure of evidence, it doesn't actually work like evidence. So you have to be strict with yourself with the p-value.
Can I take you back a bit to the robustness region
Yeah.
example you were giving? Particularly, I was really interested in how you showed that the default prior gave the wrong conclusion
Yes.
essentially on versus
Yes.
a sort of a properly formed prior. I was wondering, as a hypothetical, if you're a reviewer for a journal, how would you pick out that wasn't right? Would it be enough to show the robustness region and go, well, this isn't robust, or do you need to sort of think deeply about the problem in order to pick it out?
Yeah, in fact, you don't have to think too deeply. If all the person does is use a default Bayes factor, you just say to them, please justify why a scale factor of 0.7 is relevant to your scientific context. You can't just pluck it out of the air, and that's it. So that's enough. Oh, I took the slide out. I did have a slide here that showed what the Cohen's d of 0.7 implied in terms of raw effect size in this case, and it's outside the robustness region. So if you've been thinking in terms of raw effect sizes, you'd have seen the Cohen's d of 0.7 actually was in no way plausible.
Yeah, because you physically couldn't observe minus 3%.
Yeah, or it implies a maximum is well over 50%
Yeah.
when that's the top of the scale, and so on. So, I mean, that's one reason why it's useful to have raw numbers. It's actually easier to spot when things are unreasonable, because the Cohen's d is really just a signal-to-noise ratio. Normally, theories don't care about signal-to-noise because noise is a feature of your design. Like, the more trials you have, the less noise you have. The theories don't make predictions. That's irrelevant to the theory, per se. Yeah.
Intuitively makes sense that
Right.
factors are going to mitigate the trial. I'm just obviously it's about making people assess across all psychology.
Yeah.
Are you seeing an increase in?
Yeah, so ideally there would be some empirical study that would back up my claim, which is essentially an empirical claim. I don't know of a study that does that, but what I am seeing, and you may be noticing, is more non-significant results being published and more Bayes factors being published. And often when someone tries to publish non-significant results, an editor or a reviewer will say you must do a Bayes factor for that. So it's just my anecdotal evidence that I think that really is changing. But you're right, a proper sort of survey would be good to back it up.
I think with Bayes, the replication is a more robust sort of analysis method. So it's almost shaming the people that don't use Bayes into using it.
Yes.
Which is a good, some people just do it to make it look like they really check for the Bayes when they do it properly.
Yes, yes.
So it's a step in the right direction, I suppose.
Yes, that's right, yeah. I think we'll have to go through a period of maybe 10 years. People will be using Bayes but don't quite understand it.
Yeah.
But it's just a learning curve, isn't it? So, yeah.
I have seen a paper recently, and they just looked at Bayes. They did a parallel group design, and they just did that Bayes to check baseline differences.
Mm-hmm.
But they didn't do it anything else in the paper.
No.
Yeah. So they just sort of thought, okay, that will prove that they were matched. But they didn't actually do any Bayes when they were trying to prove there was an effect or not.
No. Yeah.
Which is like,
Yeah. As I say, I have a B for every P, so every test is Bayesian for me, which is the better way.
Any other questions? No? Well, thank you very much for the time.
Okay.